Well, everybody, welcome to yet another exciting day in community of algebra. Let me say that I've been working on a great proposal. Got to finish up, but I should be done today. So the upshot is I haven't posted your lecture from last time. That's coming today. So, and hopefully after all this, I'll get caught up on all the other stuff. Any questions before we get started? All right. This is where we left it last time, by my foggy recollection. Okay, well, before we do this, I'm going to take like a little side step here. Let me first remark that this is going to help us in our quest for this proposition. The first thing that I want to remark is if you have a principal ideal domain, it's a G domain if and only if it's semi-local. So I'll come up here, R. Suppose R is semi-local with and let me also say it's not a field, because if it's a field, it's clearly a G domain. And it clearly satisfies this. With non-zero prime, P1, these are the prime vector sets. All right.
Can I ask you a quick question?
You bet.
Do you know what the G stands for G domain? Yeah, I was wondering that all last class, so I was like, why G?
Yeah, G, don't know. Yeah, I don't know. I think at one point I did. It's probably somebody's name. I'll look that up.
Just a long name or something.
Look, I understand it. I understand the curiosity. Actually, I'm something of a collector of stamps, and I saw this. I've got something in my collection. I collect old Americans on cover. I got this cover from 1903. It was postmarked in some place in Georgia, December 25th, 1903. Now, I find that a little bit unusual because most post offices I know are closed on Christmas Day. So actually, I called the Chamber of Commerce in the city that canceled. So can you figure this out for me? But anyway, so I understand. Long story long, as it always is with me, I understand your curiosity about G domain. So I'll see if I can find
It's
out.
Goldman, Oscar Goldman.
Is it? It's Goldman?
Oscar Goldman.
Okay, yeah.
Okay,
Thank you.
cool.
Wikipedia for the win.
And actually, Oscar Goldman was also the guy that sort of handled the $6 million man. So you should probably look that up too. So suppose R is semi-local and not a field with non-zero prime P1, P2, Pn. Can somebody tell me how I showed that this is now a G domain? Remember, one of the equivalent ways to think of a G domain or a Goldman domain, I'll try to remember that, is I only have to join one element of the quotient field to get all of it. So what's the thing here? There you go, that'll work. Right. Because now, here's what happens, because you invert this product, you've inverted all the primes separately, right? And so now you've killed all the primes, and so the only prime surviving in the extension is just zero, so it's field, right? So that's easy enough. let's try to composite it on this. Suppose, R as infinitely many. So, infinitely many times. That's good enough. How are we going to show that it can't be a D domain?
Something and show that.
That's essentially it. If R is a G domain, then K is equal to R conjoined with U for some so let U with GCD because remember, this whole thing here is a PID. Right? Note that well, that's clear enough by the way I defined it. And it's certainly true that that's clear, I think. Because when you join AB, I mean, it's certainly subsumed by one of the things, right? Subsumed, I guess. What's not clear perhaps is the other containment. So can somebody explain why? That's right, and in a PID, it's actually a Bayesian condition, right? So that is to say. There's something stronger going on because we're living in a PID, and so there's a linear combination of A and B that equals 1, right? So that's very useful. Now, divide by B. Right? And notice that this piece is, this is R A B, and we have equality. Okay. And so now, after all that effort, I've kind of sort of simplified what I'm looking at now. Well, my claim is B, well, let's write. Let's factor B in our primes. Now, since R has infinitely many primes, Since R has implementing files, there exists Q and R such that non-zero, say, such that Q does not divide P. So, yeah, one over Q and then R one over B, and there exists R and R. Such that, by the way, what does a typical element of R adjoint one of B look like? Well, in general, so let me do a little scribble over here. In general, a typical element should look like R0 plus R1 plus R2 RM. Agree? But there's a more economical way that I can write this. Anybody see it? Algebra, the steady rewriting thing. Right. I can certainly write this as right, because I can find B to the M as a common denominator. And then this linear combination of lower powers of B is just some other element of R up here. So I can certainly write this. So back to here, this means that 1 over Q is R over B to the M for some R and R. Therefore, B to the M equals QR. So Q divides B to the M divides Q divides B, which is a constant. That gives me the other direction. So this will be useful. A PID is a G domain if and only if it is semi-local. Okay, questions? Yes.
So in this problem is R any commutative ring with one?
No, ours is PID.
R is the PID.
Yeah, that's super important. Yeah, I mean, who knows what happened there? We're doing okay.
Did we already prove that PIDs always have infinite primes?
No, the PIDs don't necessarily have infinitely many files. For example, any Noetherian valuation domain, F power X, or here's something. Pick your favorite number, 17. Suppose I want a PID with 17 primes. Take the integers and take the first 17 primes that you encounter in the integers. Look at that union of ideals, right? The union of ideal 2, 3, 5, whatever the 17th prime is. Look at the complement of that union, and that's a multiplicative set. Take Z and localize there, and the only primes left over will be that list of 17, 2, 3, 5, etc. Right. Yeah, PIDs can be. And in fact, if you look at something like polynomials over reals, right? Every polynomial in the form x minus alpha, where alpha is a real number, is a prime. And so there's a lot of them. So, oh, right. So a PID is a G domain if and only if it's semi-local. That's going to help. So let's do the proof of 434. Rx is never a G domain. Well, if Rx is a G domain, we had a result last time that said that any overring of a G domain is a G domain. And I want to pick my overring sagaciously. Okay, this is the closest field of R. Everybody okay with that? So it will suffice to show K of X has infinitely many primes. Where K is a field. Alright? And I really love this. Is really kind of cute. One case, there's a natural way to divide up the Ks, right? So K can be any field. So what I'm going to do to finish this proof off is I'm going to show you all that if K is any field, then the PID KX has infinitely many primes. One case is easy. Can anybody put their finger on something we can eliminate right away? What condition on K will give this automatically? Okay. Okay, if K is infinite, I can basically parameterize a large number of primes. How can I do this? Set elements, right? The elements are all right, because if you take KX, you multiply, or you mod out by X minus A, we cover the field K again. So if they're prime, and of course, the quotients of field are maximum, no surprises here because it's PID, right? Now, this is where it gets a little stickier. What if K, what if K is fine? Now, some of you number theory junkies out there might be aware of the fact that if you have like even something on CP, there's actually, in fact, if you have any finite field, there is an irreducible polynomial degree n for every n over that finite field. Right? And so if you remember from field extensions of finite fields, you can always construct, if you have any finite field, you can always construct a field of degree n over it. Agreed? And that field will be generated by a root of polynomial degree n that's necessarily irreducible. So that's kind of the fancy Galois theory, number theory way to think about it. If you have a finite field, then there's an extension of that of degree n, and that degree n extension is generated by a single root of polynomial that must be irreducible to degree n. So you've got irreducibles of bigger degree. But I'm going to do something that's a little more primitive. It may take us back a little bit. And this is actually Euclid, so I'm ripping off Euclid here. Note for non-zero polynomials in KX, polynomial is prime if and only if it's reducible. So if we're talking about non-zero is important here. We're talking about non-zero polynomials, then a prime polynomial is irreducible and an irreducible is prime. To get this direction, irreducible plus prime, you definitely need this to be KX, unique field. suppose there are only finite remaining primes. Okay, and these are prime polynomials, right? Now consider and let me point out that the degree of each of PI is greater than or equal to 1. Right, because there is no, there are no primes at degree 0 because this is over a field, those are all units, right? Consider this polynomial. Degree of this polynomial the only difference between this and this, you're adding 1 to it. Since all these polynomials are degree bigger than 1, this isn't going to affect the degree, right? Which is the sum of the degree of PI, which is greater than degree PI for all I. Hey, it's much greater. In my opinion. Oh, well, I guess if n is bigger than or equal to, but we can assume that n is bigger than or equal to. Somebody tell me a quick way that we can make that assumption. I know of 2 polynomials automatically in Kx that will be prime that are distinct. There you go. Those 2 polynomials will be in the list for sure. Right, x is prime and x plus 1 is prime. And actually, it's kind of funny because if it's a finite field, that's all that I'm guaranteed, right? Because if it's I can't add anything else other than 1 if it's characteristic 2, or I don't know that I can. Okay, so far. Note. It's going to be divisible by any of the PIs, because if that thing's divisible by, say, PI, that means that 1 is divisible by PI, which is a contradiction. Right? But the n of 1 must factor into your identicals. In fact, primes, right? But none of the PIs divide this. So P1, Pn plus 1 must be a new irreducible. This is a contradiction. If you notice, this is exactly the same classical Euclid proof that the integers have equally many primes. All right. And so the advantage of this is you don't have to know anything fancy. So I talked you through one where you can use a little bit of kind of finite field theory, or this one is kind of more pedestrian, but it's interesting to see it used in this context as well. So Kx is a PID with infinite primes. So not a G domain. Therefore, neither is RS. Okay. Any questions so far? Notice that, also, there would be something different going on if we were talking about power series, right? Because if you look at K power X, that actually only has one prime. Okay, so proposition 435. So, but R inside PB domains, with T algebraic over R. By the way, these are domains, so what do I mean by that? I just say the function field of T is algebraic over function field of R. So this is something a little looser than integrality. So when I say T is algebraic over R, what I'm really saying is the quotient field of T is algebraic over the quotient field of R. Right? And suppose the T is finitely generated over R, it's a ring. That is to say, if I take R and adjoin finitely many elements of T to it, I can get T, which is a finite number of steps. Then R is a G domain, if and only if T is a G domain. If and only. So what this says is if T is algebraic over R, right? So that means that there's basically anything here will satisfy an algebraic equation over T if you like, because you can rationalize the quotient fields. And if T is finitely generated over R as a ring, so they're close together in a certain sense, then this is enough to seal this up. That is, R is a G domain, so R is very close to the quotient field, if and only if T is also a G domain. So I think that this is, intuitively one would hope that this would be true. But let's go through the proof here. So let me introduce some notation. I'm gonna need some quotient fields here. Let K be quotient field of R. And L the quotient field T. Right, so let's suppose that R is a G domain. This way. Suppose R is a G domain. And K is R adjoined the inverse. Then take T and it to join U inverse. I just take that same U inverse and glue it to T. This is a domain. And is algebraic over K, right? Because again, U inverse is still in K, so the quotient fields of T and K don't change, and so this is again algebraic outbreak of K. And so. Right, so this necessarily has to be a field. We proved this result earlier that if you have a domain that is outbreak over a smaller field, then it itself has to be a field. So. Oops, TU inverse. This has to be a field. And it's contained in the quotient field of T because U is in the quotient field of T because it's the quotient field of R. So this is actually equal to L. And so that's all you need right there. So that means that T is G. Let's point out that nowhere in this direction did we need the finite generation of T over R. Right, so all we needed was the other hypothesis. We didn't need that T is finitely generated to get R as a G domain implies that T is a G domain. So I bet we're going to need it for the other direction. So for the other direction, suppose T is a G domain. And let the quotient field T, that is L, be T of a joint V inverse. So now V inverse is something in T's wheelhouse. And suppose that T is R. Suppose also the T is R joined U1, U2, U3. And note the elements. So we have some elements that are players here that are going to be important to us, namely V inverse and the U's. The elements V inverse and all the U's are all over R, right? Because they're all contained in the quotient field of T, which is outbreak over R. So we've got that going for us. So let me write down some equations. I'm not going to write down the whole equation, I'm going to use the leading coefficients. So we write down these algebraic equations for V inverse and all these U's, concentrating on so what notation am I going to use here? We'll say that we have A V inverse, A V minus M plus 0, and what I call VIUI. With, of course, these coefficients can all be construed to be an R. Now, if we enjoin Well, A inverse. And on the VI inverses. How many of these do we have here? So what I want to do is basically, here are the equations. This is the one for V minus one, and these are all the equations for UI. What I'm going to do is I'm going to say, I'm going to take these leading coefficients, and I am going to take the inverses of them and stick them to R. By the way, what's that going to accomplish for me? So let's suppose that we look at this ring here. So we have R. And this is of course N. Okay. So what do you suppose the purpose is? What can you now say? So these equations are algebraic, if you will, over R. Well, what can you say about the equations over R1? So if you view this, if you view all these equations instead of in R, but in this step up that we've done here, what can you say about these equations? That's right, they're integral, right? Because now you're leading with a unit, right? And so you can get rid of that for free, right? So that's kind of an important piece of the strategy here. So notice that L is generated over R. By the inverse, yeah, U1, U2, up to UN, hence, L is generated by these elements over R1, bigger ring when we stuck on the inverse of the leading coefficients. Right. So these elements, the inverse U1, UN are integral over R1 and so L is a field integral over R1. So R1 is so our conclusion here is that so K is finite over R, and so R is a G domain. Okay. Okay, any questions so far? Okay, so I'm gonna leave the next one for, an exercise, I think. Proposition. So we're not quite there yet, but here in a few resolve, what's gonna happen is you're gonna see this kind of taking a polynomial event. And this is where the Nullstellensatz is gonna come from. Let R be a domain. And U, an element of a larger domain. And by larger domain, I just mean some other domain that contains R. It could be R itself even, although in that case, this theorem is going to be trivial. If RU is a G domain, then R is a G domain. And U is algebraic. Overall. So see if you can use what we've tied together so far and prove this. We'll leave that as an exercise. And we'll move on to proposition or theorem 437. This is the first one where we start to kind of reach into polynomials a little bit. This is an interesting characterization of G domains in terms of contracted ideals with a polynomial ring. The domain R is a G domain. If and only if there exists an ideal M and Rx such that M is maximum and intercept R is equal to 0. So a domain is a G domain if and only if you can find some maximal ideal in Rx that intersects down to 0. Anybody picture such a thing? Actually, so I want to kind of see if we can wrap our heads around this condition here. By the way, when you have a prime ideal, sometimes these are collectively called uppers to 0. When you have an ideal in a polynomial ring, prime that intersects down to the 0 ideal below. All right. So the stupidest example in the world I can think of G domain is the field itself. And I can think of a bunch of ideals that intersect down to 0. In fact, I think over field, all ideals, all maximal ideals intersect to 0. Because maximal ideals are generated by a polynomial of degree 1 or greater. And if you look at multiples of polynomials of degree 1 or greater over a field, it's just going to be bigger polynomials. So no constants. Right, the only thing when you intersect down is 0. But for example, we know that Z is not a G domain. You're not going to find any ideals of ZX that intersect downstairs to 0. By the way, that's kind of a fun thing. So here's kind of a little exercise. Ask yourself this, does anybody know, do you know what the maximal ideals of ZX look like?
Find and X put together.
Right. It's a little bit more general than that. So if you look at M intersect Z, this is, I know this for a fact. Its intersection, because the maximal ideal here is the prime ideal, it has to intersect down here. To either the ideal 0 or the ideal generated by some prime. Now, if it's maximal, that one can't happen, because we know Z is on G domain. Let's see if you can work through that 305. This is impossible. So here's what happens. Your maximal ideal, find this prime here, P. That's one of the generators. And the other generator will be from Fx, where if you reduce X, it's an irreducible polynomial. So for example, the ideal generated by 2 and X squared plus X plus 1 is a maximal ideal. And there's all kinds of crazy stuff in it, right? But what about can anybody think of a maximal ideal? That's a G domain, right? We've run across this in our travels, right? Anybody find a maximal ideal? In the polynomial, right? Gotta love that. Polynomials will all coefficients being power series, but it's not so bad. Such that power
And oh no. That's
you might see a principal ideal that does it?
the ideal generated by X,
By what now?
by X.
Well, if you look at the problem here is that's not going to be a maximal ideal. Because when you kill X, it's not a field. Yeah, X is not quite big enough. Look at this. Look at the ideal generated by X t plus 1. Now let me be a little bit sloppy with this. But what happens when you mod out by this ideal? This is basically in the quotient field, this is like, well, -1/x, right, when you mod out. So basically what you have is q power x adjoined with -1/x, so you get a field. So this should be a maximal ideal. But now it's fairly easy to see that the intersection of this with q power x is not, I mean, don't let the q power x mess you up. This can be just anything right here. This is an element from here times t. When you multiply this by any other polynomial, its degree is going to be 1 or greater. So there's no constant term except for 0. Like, this is kind of weird, right? And you can't do that over here. What if you tried to do something like this? What if you modded out by this? right? What if you look at ZX, because this is basically the analog of what we did here, right? What happens when you do this? Basically, when you take ZX and you mod out this, what you're doing is you're turning X into 1/2, right? And so now what you have is a small string containing Z and also containing 1/2. So you've got plenty of primes left over. All the odd primes are left over in that quotient. So there we go. That's a good example of this right here. We'll prove this next time. But is everybody kind of understanding the puzzle on that a little bit? It's kind of a weird example because the reason you can do this is because of the fact that this is local and this one's. Okay, questions? Questions? Any questions out there? All right, well, I will have the lecture for today and last time we'll post it soon. Y'all have a good one. We'll see you on Friday.